Hello, my name is Arjun Verma, and right now I'll be presenting my second lab for Physics 2111. So the whole purpose of this lab is to determine the motion of some object that has drag or air resistance and utilizing various modules to estimate that motion. And these models will be utilizing gravity and drag and the net force of those two in order to estimate the object's motion. So obviously when any object falls, it has the force of gravity acting on it. And our most basic model will utilize that force of gravity to predict the updates in velocity and thus the updates in position to model the position of the object. And then we'll have more complex models that utilize drag, which is proportional to the square of the speed of the object, as an update to the net force on it, which will thus update the velocity and the position of the object as well. And we'll be illustrating the effectiveness of these multiple models versus reality or some real data. So getting to that real data, it was collected by taking a recording of me dropping a regular piece of 8.5 by 11 inch paper, and that object was tracked using tracker after a video was captured using a smartphone. And the tracker, image and collection scene can be seen to the right, and the y-axis, like the paper ty, is what we're looking at because we're looking at how the y value of the paper changes as it drops over time. So in order to predict and assume the position of the paper, we need to create certain models. So the models were all based off of the principle of the momentum update formula and the position update formula to update the velocity by dividing the momentum update formula by mass, and thus the position of the object. And the velocity of the object started at 0, but we also utilized the momentum update formula in order to update the velocity based off of gravity and drag. So the first model we used utilized just gravity, or mg. The mass of the paper was found. It's found to be 5 grams multiplied by negative 9.8. So we found our force of gravity. Then we divided that by the mass in order to find the update in velocity each time. So the model updated velocity as it went with that acceleration, and as it updated velocity using the momentum update formula, it also updated position using the position update formula in order to estimate the position of the paper. Then we created another model that accounted for drag and gravity, and the only way this was different is in the previous model the net force stayed the same, but in this model the net force changed each time as it was updated by the square of the current speed and some proportionality constant, which I, through some research, found to be I believe 51 times 10 to the negative 6th or 7th for paper. And what that did is it updated the net force each time, and by updating the acceleration each time, it also changed the way the velocity was updated, and it still utilized the momentum update formula and the position update formula to update position and velocity. And the net force or acceleration changed because it wasn't just gravity, it was the square of the speed each time, and as the speed got larger, the effects of drag got larger. And then our final model accounted for initial velocity, drag, and gravity, and it's the exact same as the drag and gravity model, but it just had an added initial velocity. So the models are created in GlowScript and ran multiple times, and as you can see, the net force is updated each time for drag, and it stays the same for gravity, and for both, the velocity and the position are updated each time, and the time and initial position match exactly what was put into tracker. That way it's an exact replica of the initial state, and the model can do its best to predict. So for the no drag model, it was very, very inaccurate. As you can see, in real tracker, the paper reaches 0 by the end time, and in the model, it reaches -5. So it went way farther down than it should have, and the failure started at about 2.9 seconds. And this is because it assumed no drag. So if this piece of paper didn't have any drag acting on it, no air resistance, then it would fall pretty similar to this. And this model could be drastically improved by adding drag and other effects of air resistance, and no terminal velocity could be seen. With the drag model, it was slightly more accurate. However, the drag formula given was not accurate for this situation due to the fact that paper is very difficult to handle, and its shape changes and the way it resists air changes as it falls. But a terminal velocity could be seen because if you look at velocity over time, it starts to round out and become consistent. And as well as the drag with initial velocity, it also had a terminal velocity that was able to be seen. And the terminal velocity is actually the exact same as the one without initial velocity. And that's because the initial velocity doesn't matter, because it comes to a certain point where drag and gravity are equal, and that's where terminal velocity is reached. And the initial velocity has nothing to do with that because it has nothing to do with the force applied. Comparing all the models together, you can see that none of them were really that accurate, and that's because the sheet of paper is very complex, so as it gets drag, it deforms and the drag changes. Thank you so much.